Hey guys, today we're going to be jumping into chapter 6 of our textbook. So chapter 6, as you can see, 6.1 starts with properties of exponents. It's going to be a lot of stuff you've seen before. Again, we're just building into this chapter. But what we're going to be diving into is how do we solve equations that maybe aren't quadratics like chapter 5, but cubics with x to the thirds, or quartics with x to the fourth, or even quintics or quintics. I've seen it pronounced both ways, x to the fifth. So these higher degree equations, we're going to see some strategies for approaching them. How do we solve them? What do we know about their graphs? Things like that. So before we get into the meat though, we do have to talk about exponents. And again, a lot of this will be review. So hopefully this will be kind of a nice section to start off with. And before 6.1 even, we do need to talk about, I might call it 6.0, which is scientific notation. Now this chapter kind of assumes that you have an idea of what scientific notation is, and you have seen it before in previous classes, be they math or science classes. But what I want to do is just go through these quick 3 problems. 2 of them are straight scientific notation. One of them is kind of a converting units problem. All really good things to know, important things to know as we move forward. So scientific notation, if you don't remember, is just a nice way of writing really big numbers or really small numbers. As you can see on number 1 there, no one wants to get a lab report and see the number point 0.000000005. I think I got all the zeros there, but that's the point. We can't tell easily what is that number, how many zeros are there. It's really small. So scientific notation is typically written as a times 10 to the bth power. It's always going to be 10 to the some power. We work in a base 10 system. We have 10 fingers, 10 toes. So what is this really tiny number on number 1? Well, what we do is we say, how many spots would I have to move that decimal point so that A is between 1 and 10. Okay, we want it to be a number between 1 and 10. And so I say, okay, I would need to move it 1, 2, 3, 4, 5, 6, 7, 8, 9 spots, and then I will get 5.0, and that's between my 1 and my 10. So 9 spots, that means that I'm going to say that this number is 5 times 10, and then the only question is, should it be a positive 9 or a negative 9? For really, really small numbers, they're going to be negatives. If it's a really tiny decimal, it's going to be 5 times 10 to the negative 9th power, and then we can say meters per second. So when we're looking at this, this right here is much nicer to look at. 5, and a lot of times you'll see it written just 5.0. People want it clear, it's just 5.0 times 10 to the negative 9th meters per second. That lets us know there's a 5 in there, and that we had to move that decimal place again, 1, 2, 3, 4, 5, 6, 7, 8, 9 spots to reach a number between 1 and 10. Now our calculators do sometimes work with scientific notation as well. So on our calculator, we can see scientific notation in action. If I type this out, 0.000000005 and hit enter, the calculator will sometimes just by default simplify that, 5e negative 9. And that e stands for times 10 to the. Okay, so you'll see that sometimes on calculators. We'll see it as we go along. Just wanted you to be aware of that. Let's look at another example. 94,300,000 square inches. That's a lot. That's a really big number this time. And there is a decimal point because this is kind of 0.0, right? 0.0 is the same as just any integer. So if I want to make this a number written in scientific notation, I'm going to say, how many spots do I need to move the decimal to get between 1 and 10? I would need to move it back this time. 1, 2, 3, 4, 5, 6, 7, it looks like. And that would get me 9.43. Just that number kind of on the left, 9.43 times 10 to the 7th. And because it's a really big number, it's a positive 7. Big numbers that we're writing in scientific notation will typically have positive exponents. Super tiny numbers will have negative exponents. So positive 7 square inches. 9.43 times 10 to the 7th. Again, if I counted that right, 1, 2, 3, 4, 5, 6, 7 to get there. Looks like I did. So those are the very basics of scientific notation. There's more we could talk about. We could talk about significant digits, significant figures, as you might have in science classes and whatnot. We're going to leave it there for our purposes, though. And we're just going to solve one problem here. And here it is. If a snail can travel at a top speed of 2 feet per day, what is its top speed expressed in miles per hour? It can go 2 feet per day, and we want to go miles per hour. So this is a technique. It has a few different names. I think probably the most common one is dimensional analysis, because we're looking at dimensions, we're looking at units, and we're going to be converting. So here's where we start. We start with, okay, the snail can travel 2 feet every 1 day. And we write it kind of like a fraction, 2 feet per day, 2 feet for every 1 day. That's a ratio. So now, though, we want to know miles per hour. So first thing I'm going to do, I'm going to convert those days to hours. I'm going to multiply by however many days are in an hour, or however many hours are in a day. Now, the second one that I just said is probably easier. There are 24 hours in 1 day. Think about fractions. We can multiply something and not change it as long as we multiply by the same thing on top and bottom. That's what we did here. 1 day is equivalent to 24 hours, so we haven't changed anything. We're just changing the units. The other thing I want to point out, it was important for me to put days on top in green, because we can think of it as we want our days to cancel. Now we know that a snail can go 2 feet every 24 hours, which makes sense, which is exactly what we had. So 2 feet every 24 hours, but we didn't want feet per hour, we wanted miles per hour. So we have to multiply by something else that's going to convert the feet that we have. And I'm going to put the feet on bottom to cancel out with my purple feet on top, feet into miles. Now, how many feet are in 1 mile? 1 mile is equal to 5,280 feet. Maybe you knew that, maybe you didn't. You know, we live in Colorado, you might have heard like Denver, the mile-high city, because it's talking about the elevation. But 1 mile is equivalent to 5,280 feet. Maybe we had to Google that, but the bottom line is now my feet cancel. And if you look at what units we have that we haven't crossed out, we've got miles per hour, which is a really good thing. All we have to do now is multiply across. So 2 times 1 on top, it sounds like a snail can go 2 miles every 1 times 24 times 5,280 every 126,000, and it was 720 hours. Okay, 2 miles every 126,720 hours. That's a long time, but snails don't move that quickly, so it kind of makes sense. What I want to know, though, is how many miles per 1 hour. So I'm just going to divide those. I'm going to say, what is 2 divided by 126,720? And here, take a look at that answer. I can't write on my calculator, unfortunately, but do you see the little e at the end? It says 1.57828228 e negative 5. Remember that e means times 10 to the. So I'm going to write, and keeping with the theme in our class, I'm going to keep 4 decimals, 1.5783. I'm going to round that 2 up to 3 because of the 8 after it, times 10 to the negative 5th miles per hour. And so we can just kind of siphon off the units, if you will, miles per hour, and then divide those numbers to get our answer numerically. So 1.5783 times 10 to the negative fifth miles per hour. That means we know we would have to move the decimal back 5 spots. And so it's going to be like 0.000015783. It's going to be a tiny number miles per hour, which makes sense because it's a snail. So that was a little bit of pre-lesson. Again, things you hopefully have seen before. I'm hoping this isn't the very first time, but things you'll need to use in this chapter, in this section. So we're going to move on though to the main event, which is properties of exponents. There are a lot of things we want to talk about with exponents. We're going to kind of rocket through a bunch of these. And by the end of the lesson, we'll be able to kind of simplify and solve all of these expressions really comfortably, hopefully, once we know our exponent rules and we've refreshed them. So I'm going to start here with negative exponents. How do negative exponents work? Well, I have a couple things written there. 2 to the negative first power is the same as 0.5. 2 to the negative second power is the same as 0.25. 2 to the negative third power is 0.125. How does this help us? Well, I'm going to write another thing here. I'm going to say, what if we wrote these as fractions? 0.5 is just 1/2. We know that one. 0.25 is 1/4. 0.125, if you're not familiar with this one, that's 1/8. So there is a little bit of a pattern going on here. You say, okay, so it like the denominator doubles every time. I'm going to write it one more time, and this is going to be the key. This is 1/2 to the first. This is 1/2 squared. This is 1/2 cubed. And here's what I want you looking at. 2 to the negative first is the same as 1/2 to the positive first. 2 to the negative second is another way of writing 1/2 to the positive second. 2 to the negative third is the same as 1/2 to the positive third. So if I'm writing a general rule, I'm going to say that a to the negative bth power is the same as 1/a to the positive bth power. 1/a to the positive version of that exponent. So couple examples here, and these rules, I mean, a lot of them you're going to have to write down. We are going to have them memorized. And so we're just going to get a little bit of practice with each. 5a all to the negative second. Well, when I see that, one of the first things I'm going to do is say, well, that's 1/5a to the positive second. Once I put it down in the denominator, it's no longer negative, it's just positive second. So 1/5a squared. And we can do that. That's 1/5 squared is 25. A squared is a squared. And there's our answer. 5a to the negative second is 1/25a squared. What about 5 times a to the negative second? Well, that means we have 5 times 1/a squared, using our negative exponent rule that we just looked at. But notice that the -2 only applies to the a. So 5 times that, we could say, well, this is 5/1, so these are fractions, multiply straight across. 5/a squared. So just making a couple points here. One is our negative exponents rule, what it is. And the second point is, be careful with the parentheses and see what does that exponent really apply to. Okay, so that's negative exponents. What about multiplying or dividing expressions with exponents? And we've seen this already this year, except we're just going to get into a little trickier territory now. A squared b cubed c squared times 5ab squared c squared equals 5a cubed b to the 5th c to the 4th. So how do we get there? What is this rule? First thing we do, we multiply the numbers. 5 times my invisible 1 here gets me 5. But then what about my a cubed? Where did that come from? Well, a squared times a is a cubed. And we kind of know that, but the formal rule is we're just adding those exponents. A squared times a to the first, there's that invisible 1 we don't write when it's to the first power, 2 plus 1 is 3. A squared times A is A cubed. B cubed times B squared, if you add the exponents, 3 plus 2, we get B to the 5th. And then C squared times C squared, we add those exponents, C to the 4th. So notice we are adding the exponents of each variable as it's multiplied by that same variable in the other expression. So general rule here, A to the bth power times A to the cth power is going to be A to the B plus C. We add exponents when we are multiplying two expressions with the same base. What about dividing? Multiplication and division are kind of opposites. So what is the opposite of adding those exponents together? We are going to subtract them. Numbers, this doesn't apply to, only exponents. So 6 divided by 3 is where we get our 2. But then A to the 4th divided by A, we subtract those, that's an A to the 1st on bottom. So A to the 4th divided by A is just A cubed. B to the negative 3rd comes because we had B squared over B to the 5th. B to the 2 minus 5 is B to the negative 3rd. And then a similar story here with C over C to the 6th. C to the 1st on top, C to the 6th on bottom, 1 minus 6 is negative 5. So when we are dividing expressions with exponents that have the same base, the exponents, it's top minus bottom. A to the B over A to the C is equal to A to the B minus Cth power. Now I also want to show you a couple other ways. One to write this and one to solve it. So I'm going to take this same problem that I just had up here and write it again. 6a to the 4th b squared c over 3a b to the 5th c to the 6th. And I like showing this because conceptually I think it makes a lot of sense, but it's not a very efficient way to do anything. So see if you agree with what I write here. 6, I want to keep the color coding the same. Times a times a times a times a. Then we went red times b, and then we went dark purple times c, all over 3 times a times b times b times b times b times b. Should have made this a smaller number, times c times c times c times c times c times c. Okay. Well, this is why this rule works, is because what happens here, those a's cancel, 2 b's on top cancel with 2 b's on bottom, this c cancels with the c here. So we have 6 divided by 3, we know that's 2 on top. We have a cubed on top because we have 3 a's left. And then we have change colors, b cubed c to the 5th on bottom. Now, is this fraction that we just wrote out exactly the same as what's on the left side of the screen? The answer is yes, because remember our negative exponent rule? We could have written this as 2a cubed, but then b to the negative 3rd drops the b cubed down to the bottom. It just drops it to the denominator and makes it positive. B to the negative 3rd is 1 over b cubed, so we can put that there, c to the 5th. So here's the bottom line. This is a great way of writing it. This is another great way of writing it, the 2 rainbow boxes that I just put on there. Sometimes one will be more convenient than the other. Sometimes the other one will be convenient. So it's good to realize that, and it's also good to see where this rule comes from, how we're just canceling variables, and that's why we subtract the exponents. So that leads us to our rule, a power of a power. How do we take the power of a power? A to the 4th to the 6th power is a to the 24th. And so what did we do there? We just multiplied. A to the 4th to the 6th power is a to the 24th. That means the rule is a to the bth to the cth power. Our general rule is just we multiply those, a to the b times c. Now, what if we had a power of a product or a quotient? AB squared, all cubed, we kind of just distribute that power. A cubed is a cubed, b squared cubed, power to a power, so I multiply them, 2 times 3, b to the 6th. If we have a quotient, a over b cubed, we just cube top and cube bottom. A cubed over b cubed, with the one caveat, assuming that b does not equal 0, because if it did, we'd be dividing by 0 originally, and that can't happen. We know that dividing by 0 doesn't work. But the point being that we can just distribute this power to top and bottom of our fraction. We just get a cubed over b cubed. So things we've actually seen, things we've kind of done already this year, just wanting to formally lay them out and then get us to our last rule. And this is kind of a weird one, but this is a really important one for you to know. What is a to the 0th power? A to the 0th power is 1, provided that a is anything but 0. Why is this? Because it seems like it should be 0 if we don't have any a's or something. A to the 0th power is 1. Let me give you a quick, it's not a proof, but it's some reasoning why this is a thing. So let's say, let's do powers of 2. 2 cubed equals 8. 2 squared equals 4. 2 to the 1st equals 2. 2 to the negative 1st we saw today is 1 over 2. 1 over 2 to the 1st power. 2 to the negative 2nd is 1 over 4. What is happening in all of these? Well, how are we getting from one to the next? We're dividing this by 2. We're dividing this by 2. And to fill out the pattern, what is 2 divided by 2? We're going to make it 1. Anything to the 0th will just be 1. And you can see now this pattern holds all the way through, positive integer exponents or negative exponents, all of them. We could do the same thing with 3's. I'll say 3 cubed is 27. 3 squared is 9. 3 to the 1st is 3. 3 to the negative 1st is 1 over 3 to the 1st. 3 to the negative 2nd is 1 over 3 squared, which is 9. Sorry, I've just been writing that. Which means to make this pattern hold and to make the math work out, 3 to the 0th has to be 1 so that I can say, well, I divided by 3 here. 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 That 0th power serves as sort of the bridge from the positive exponents to the negative exponents. So the good news is you don't have to understand necessarily, you don't have to be able to explain what's on the screen right now. What you do need to know is that anything to the 0th power is 1. So I want to work kind of one long example and then all those rapid fire examples I had at the beginning of this of the lesson, and then we'll call it good. And I want to work this one in 2 ways. Simplifying 3x squared y over 2xy to the 4th, all cubed. Now, I want to show you that you can work this either way and it still works out okay. In red, I'm going to cube both top and bottom. So I'm going to say, okay, so 3 cubed is 27. X squared cubed is x to the 6th. There's my power to a power. Y cubed is just y cubed over, on bottom, what is 2 cubed? 8. X cubed is just x cubed. And y to the 4th cubed is y to the 12th. So I could cube first. Then I could say, okay, well, 27/8 doesn't simplify. X to the 6th over x cubed. With our dividing rule, we subtract those exponents, so that means x cubed. And y cubed over y to the 12th, again, we'll use our dividing rule. I'll subtract those exponents, y to the -9th. Or I'll just show you that alternate way of writing it with y to the +9th on bottom. Okay, we are perfectly able to cube things first. But what if we didn't? What if instead we said, well, let's simplify what's inside there and then cube? So that means we have 3 over 2. We have x squared over x, so that means we have x here. And then we have y over y to the 4th. So that's, if we cancel out one y on top and bottom, that gives us y cubed on bottom, right? So we could like kind of simplify this and then cube it. If you want to write it, again, I'm just showing the alternate way to write these negative exponents. We could say, or 3/2 x y to the -3rd cubed. Both of those work out. Both of those work out fine. They are exactly the same thing. Pause it for a second if you don't quite see it. Make sure you understand why. So then if we cube it, we get 27x cubed on top over 2 cubed is 8, y to the 9th. And again, alternative way of writing it, 27 over 8, cube that fraction, x cubed, y to the -9th. And as you look, both of these generate the same answer written both ways, with negative exponents or as a fraction. So we can simplify inside first if we want, and then cube the whole thing, or we can cube the whole thing and then simplify. And that's kind of nice that we have that option, whichever one looks easier, seems easier to you. Okay, so here we go. Rapid fire. I just want to work all these and throw all of our rules together. I'm going to go kind of in just a random order. I'm going to start down here. A cubed b, all to the 5th power. Well, a cubed to the 5th power to a power, we multiply a to the 15th. And then b to the 5th is just b to the 5th. Just like that. What is 4 to the -3rd power? Well, that would be 1 over 4 to the +3rd. 4 to the +3rd, 4 times 4 times 4. If we're not sure, I might use that calculator 4, the caret to get up there. 4 to the 3rd power is 64. So this is 1 over 64. Let's go left. Let's go left and say, what is 2ab cubed? 2 cubed is 8. A cubed is a cubed. B cubed is b cubed. We'll go up and say 14a to the 7th over 2a cubed. First, we'll divide the numbers. 14 divided by 2 is just 7. And then now let's use our dividing exponents rule. A to the 7th divided by a cubed, we subtract those exponents, top minus bottom. A to the 4th. 7a to the 4th. I'm going to go bottom right now. 3b over a, all to the 4th power. Well, let's just apply that power to top and bottom. What is 3 to the 4th? 81. B to the 4th over a to the 4th. And that one's simplified. And then last one. Let's multiply some of these together. C to the -3rd times a squared times ab cubed. I'm just going to multiply again, like we did. A squared times a is a cubed. That's 3 a's being multiplied together. B cubed, there are no b's to multiply by, so it's just b cubed. And c to the -3rd, there are no c's to be multiplied, so it's just c to the -3rd. And then, just for fun, I'm going to write that the other way we could write it, in case you are fond of this way, you're going to have to be familiar with both. A cubed, b cubed, over c cubed. Both are fantastic ways to write it. That's c to the negative third. All that means is that the c cubed is on the bottom. So guys, I mean, that didn't take us long at all to do 1, 2, 3, 4, 5, 6 problems. When you're looking at your practice problems, it might look like a lot, but they do go pretty quickly. You do have to know these exponent rules. This is really important that you get these down. Don't even have to think about them. So go back, rewind, pause if you need to. Let me know if you have questions, and then get lots of practice making sure you are super comfortable with these exponent rules. So hopefully this was kind of a little bit of review mostly. If you have questions, write them down so you know to ask them next time we are together. But otherwise, take a look at those practice, and then we will use this as a springboard for 6.2 and the rest of the chapter.